In the last lecture, I gave you an example of the beta binomial conjugate case in which I showed you that you can easily derive the posterior by just multiplying out the likelihood and the prior, and you can choose different prior specifications for theta. So today, in this lecture, I'm going to talk about another conjugate case, which is the Poisson-Gamma case. Okay, so the example that I want to work with is some real data that comes from one of my old papers. What we have is from an eye tracking study. So we are looking at reading times when people are reading sentences on the computer screen. You can record the number of leftward eye movements that you make from a particular word when you're reading a sentence. So that's what the data look like, right? You would get some discrete values 0, 1, 2, 3, 4 that would tell you the number of regressions that you're making at a particular word in some particular condition and for some particular subject or item and so on. Okay. So how would I analyze this data? Well, first of all, if you take a look at the data, if I look at the summary, I see that the data has a maximum value of 21, minimum of 0, lots of missing data. We can ignore that for now, right? And although I'm getting a mean of 1.165, the actual numbers are discrete numbers here, okay? You can't get 1.5 regressions, regressive eye movements in a particular word. So because the outcomes are discrete, right, we're going to model it using some kind of discrete random variable. And one useful random variable you can use for this particular type of data is the Poisson distribution. So the Poisson distribution is defined as shown in equation 1, right? It's got a parameter lambda, which is the rate parameter, the rate at which you do those regressive eye movements, right? And of course, we don't know what this lambda is, right? It's always a question of estimating it from the data, and x is the data here, okay? And x factorial here is, I assume that you know what this is, right? X factorial is a mathematical term here that should be familiar to everyone, right? Okay, so how do I go about doing a Bayesian analysis given some data of this type, right? So we're going to just simulate some data because I don't want to work with the complexity of the real data right now. Just to illustrate the point, suppose I have 10 data points that are coming from some lambda distribution with some unknown lambda parameter, right? So these are the data points that I've generated randomly. This will serve as our data now, okay? So that's an example. So these are the 10 data points again. You can see that they have this discrete distribution. So I put the points here because there's nothing between 0 and 1, for example, right? That's why this is a discrete distribution. Okay, so now let's assume for now that prior research on the topic of leftward eye movements, or maybe expert knowledge, there are many eye tracking experts in the world in psychology and other areas, suggests that the prior mean of lambda, so the rate of regressions, is 3 and the prior variance is 1.5. Okay? So this could be a possible prior knowledge that we have from previous work. So the first step that we will take is we're going to have to define a prior distribution, a PDF, for the rate parameter lambda in our Poisson distribution, right? Because we're going to carry out that multiplication, likelihood times prior. The parameter is now not theta but lambda, so I'm going to have to define a prior for lambda, right? And this prior has to reflect, or should ideally reflect, our prior belief or knowledge about lambda before we've seen any new data, right? So it turns out, okay, it just turns out that one good choice for a prior for the lambda parameter is the gamma distribution, which I will explain in a minute. The gamma distribution is a continuous distribution, which is again defined in terms of two parameters, a and b. Okay, so they have different names in R, but in statistics you will see that it's generally defined in terms of some parameters called a and b. Right now, at this point, usually people start getting nervous about prior specification, and people keep asking me, my students always ask me, well, how do I decide what the prior is going to be? I'm going to talk about that later. Right now, we're going to rely on our prior knowledge from some expert, these prior mean and standard prior variance, right, tells us what possible values lambda can have, and we're going to use that to define the prior for now. Okay? So what does the gamma PDF look like? Well, this is what it looks like. for any random variable x, right, with parameters a and b, this is the definition. Notice that x has to be larger than 0, so the rate cannot be less than 0, right? So we're going to be modeling the rate parameter lambda using this gamma. So instead of x, we'll be using lambda here, right, because we're modeling the lambda parameter, and it has the right property, this gamma distribution, that rate cannot be less than 0. Okay, so this is the form of the distribution, and the details actually don't matter to us right now. Okay, as you will see, it all simplifies, and everything works out very nicely in these kinds of analyses, right? Okay, so in R, as I mentioned, A and B have different names. They're called shape and scale respectively, right? So you could actually simulate data. For example, this is R gamma I'm using. Remember the DPQR family of functions? For gamma, I have it too. So I've generated 10 data points which are producing simulated data from a 3 and 1. A and B is 3 and 1, right, distribution. And so you can see that this is the type of data that I would get. So the reason I'm showing you this is that when I'm actually doing data analyses, I actually generate some simulated data from my priors to see whether they reflect my prior belief adequately or not. So just drawing out the prior distributions graphically is a good way to understand what you're actually asserting about plausible values about the prior, about the parameter. Okay, so this is what it looks like, right? The 3-1 parameter. So in a practical setting, if I was actually analyzing data with regressive eye movements, I would look at this and check whether this reflects my prior knowledge about leftward eye movements. So I've been doing eye tracking work for 20 years, so I have a reasonable idea of what the range of variability might be in leftward eye movements. And experts in eye tracking generally know this too, or can tell you about this. Or you can use prior data to work this out. Okay. Anyway, so we are now going to decide on the A and B priors, right? So we first need to figure out what these parameters A and B are going to be, right? We have to decide on these. Now we already know something. We know that the mean and the variance of lambda from prior research, the mean is 3 and the variance is 1.5. What we also know, well, I didn't tell you this, but we know this from statistical theory, is that in the gamma distribution, the mean of the gamma is A divided by B, and the variance of the gamma distribution is A divided by B squared, right? So this is very cool because I have two variables A and B, and I have two equations now that I can write out. So all I'm going to do in the next lecture is that I'm going to simply carry out this calculation and figure out what A and B is given these two equations and given these two values for those two equations, right? So we're just going to solve for A and B, simple algebra, and this will give us the parameters on the gamma prior that we will plug into Bayes' rule to get the posterior on the lambda parameter. Okay, so that's what will happen in the next lecture.